Мгм.
М.
Сейчас, секунду. Huh? Uh, okay, so today our speaker is Martin White from
М.
Nelson Mandela University at Port Elizabeth, South
М.
Africa. And the title of his talk is Local Nets of Observable Algebras. Three.
Local nets of which algebras?
Uh, Local nets of, uh, let me check. As far as I remember, local nets of observable.
Observable.
Yeah, just,
Наблюдаем.
да.
Oh.
Oh,
Unbounded operator algebras.
unbounded operator algebras.
No,
But
no.
from the quantum mechanical point of view, of course, they consist of observables. So
Yes.
my title was very close to Martin's mind. Okay,
Yes.
okay, Martin, please.
Yes.
Thank you.
And
I would
here
like
is
to.
here is we invited to the reason.
Martin.
Yes, I'm here.
Uh-huh.
Um, I would first like to thank all the local organizers for allowing me to give this talk as part of the seminar this afternoon.
Mhm.
I just want to see how to share my screen here.
Screener is
I see that option is suddenly not there.
no.
Mm.
His slides.
Where would I share my screen?
Mm.
Oh, there we go. Share, and that's the one. Okay, let me just see some sharing. Can you see the slide?
No.
Okay, okay, hang on. I think there was the
Uh,
share, and I'm going to go share.
oh, uh-huh. Okay,
Uh,
okay, now we
Oh,
can see it. Mhm.
yes.
okay, you can see it.
Mhm.
Yes.
Okay, thank you. Thank you very much. All
Thank you.
right.
Mhm.
All right, and I take it you can, yeah, I'm unmuted. Okay, I've just got a problem with my camera. It's on and off it. I think with Zoom it's not very compatible. So I do apologize for not having the camera on.
Well,
Okay, thank you again for allowing me to give the talk this afternoon. So what I will discuss here is local nets of unbounded operator algebras, and
mm,
I will give some motivation for this. Um, I just want to mention at the start here that I've that this work has been published last year in reviews in mathematical physics under the same title.
mm,
So if you want to go and look the paper up at some point. And also I gave a shorter and a somewhat more condensed version of this talk last year in January in San Francisco at the joint mathematics meetings.
mm.
So here in this talk, I plan to give more detail than what I was allowed to give back then. Um, Although I will not necessarily mention everything in this publication. So just I will focus more just on the main gist and the fine points. Okay, one of the things that we know about local nets of bounded operators is that you are looking at local observables which are in a von Neumann algebra. That's the one theory. Then some axioms which go with it. And then there is also the theory of Arthur Wightman, and that makes use of unbounded operators. So that is where you take the field and you represent it as unbounded operators with a distribution. I think some people prefer the local nets over the Wightman field approach because the Wightman field approach uses the unbounded operators, which some might not see as something very tractable to work with. So also in this talk, I will be looking at local nets of unbounded operators for two reasons. The one reason is that our observables are mainly actually unbounded. And the second reason is that it allows a framework in which actually to combine the local net approach with the Wightman approach. So one unifying structure for both. Okay. So I'm just going to first go through what we know about local nets of von Neumann algebras and then Wightman theory. So if we start with a local net of von Neumann algebras, that will be a mapping just from some bounded open region in four-dimensional space-time. So R13 meaning three spatial dimensions and one for time. And RO here is a von Neumann algebra. And the mapping will satisfy two conditions. If the one region is contained in the other, then the observable for the one region will be contained in the observables for the other. So the one von Neumann algebra sits inside the other. And if O1 is space-like separated from, let's say, O2, then it means that an observable in RO1 will commute with an observable in RO2. Okay, in other words, you can say that this thing is inside the commutant of RO2. And likewise, the commutant of RO1 is inside the commutant of RO2. And that's usually how one represents this sort of condition. Also, there is a unitary representation which will take you from the Poincare group into a unitary operator, but also in such a way that you've got this covariance-like conditioning condition going on. So lambda here is translation and A is a point in space. And then also UA1, if you put in, let's say, from the translation 1, then you actually get this sort of exponential going on where P0 to P3 are self-adjoint commuting operators. And then the joint spectrum of that here will be contained in the forward light cone for that. So for that four-dimensional space-time. Also, one assumes that there's a normalized vector, normally called the vacuum vector, so that if you take that same operator which we've had previously and you apply it to omega, the vacuum vector, then you get the same vector out again, no matter what. That's for all translations. In some references, one has the following condition as part of the definition of local net. So one has that the bicommutant of the union over all A will become B of H, and that's for all bounded open regions. Okay, for our purposes, it will always be understood that the previous three conditions are part of the definition of local net and not necessarily this condition 4. So it's basically then those three conditions, including the covariance condition, which we will assume. Okay, earlier on. Okay, earlier on, yeah, the A are the translations. Sorry, I misspoke over there.
Sorry, space-like separation means what?
Space, okay, space-like separated That will primarily mean that okay, that you need faster than light travel to actually get from the one region to the next. So that's actually what it means in this case.
I see.
Okay, all right. Okay, Wightman field. Now that's the other paradigm. A field operator, that's usually a map going from that. This is now the Schwartz space R113 of rapidly decreasing analytic functions into L plus of D. And D is an inner product space, and H is the Hilbert space containing D as a dense subspace. This, in actual fact, then is all linear operators. I can explain what this is here. So, and I will be going into this again in more detail later on. So we're looking here at all linear operators, which will take you from the domain into itself, and in such a way that okay, we know that it has an adjoint, and then T star, when you restrict it to D, will also map into D. And then this becomes an algebra with involution. Let's write it as T plus, and then that's just T star restricted to D. Maybe to make that more clear, I should rather write T of D. Let's use the eraser. And then T plus will be T star asterisk, which I then go and restrict to D. That's the involution. Okay, I will be saying more about it later again. And H then contains D as a dense subspace. The first thing is that the map is a star homomorphism. And then one also wants to have that if you take a function and you go to the inner product of these two vectors, omega in H and this vector in H. Okay, this is more specifically in D, but okay, in particular it's in H, that this is then also some kind of a distribution. So that's also just to bring about the smearing effect which one has at a field that maybe you can't exactly measure the field strength precisely at a point. So it's sort of like the values are smeared, and that's why one has this distribution.
No. Okay.
This is what we mean by a field operator, and also it's a star homomorphism. So that this is actually, if one can say, a star homomorphism, so that also is a homomorphism which respects the involution. So already here we are encountering a special type of unbounded representation of this infinitely differentiable functions, rapidly decreasing differentiable functions on the, and it's now. And then it's an unbounded representation. But again, I will speak a bit about it later on. Okay, that's not the end of the story necessarily. A Wightman quantum field theory in dimension D will consist of the following: a space of states belonging to a Hilbert space, a vacuum vector omega of norm 1, and a unitary representation going from the Poincaré group to B of H. Then a collection of field operators, so that's like on the previous slide. So that if you look at all phi mu of F omega with F in here, then this is again becoming dense in H no matter what this mu is over there. So the field operators here were defined as in the previous slide. So also for the Wightman quantum field theory, one has also those other three properties coming along. And then again, now we've got some axioms satisfied that need to be fulfilled. The first is the unitary representation satisfies this, as previously mentioned, especially in the local net. I've mentioned it in the local net approach. And one also assumes that this will map the domain D over that we see here into itself. And no matter what group element in the Poincare group one takes, and also like in the local net approach, one has a similar type of covariance condition being fulfilled. So that's the first thing, the covariance. So it's looking rather similar to local nets, except now one has these unbounded operators coming in. The second axiom that we have to be satisfied is that the supports of F and G are space-like separated. Then again, we've got this commutativity going on, like in the local net approach, where, okay, in the local net approach, it was something like R01. If O1 was space-like separated from R2, we had this sort of thing. And then also likewise that RO1, the commutant is contained in just RO2. And now the field operators, they satisfy this commutativity requirement when you've got space-like separated. That's the supports. And again, you've got here this thing like in the local net definition. And of course, axiom 3, like in the local net definition, the joint spectrum being contained in the forward light cone. And the only vacuum vectors in H left invariant by all of these are all the scalar multiples of omega. Of course, if it maps omega to omega, then it will take all scalar multiples of omega to omega. All right, now I've given a quick summary as to the local net approach, where only bounded operators are involved in von Neumann algebras, and then also the Wightman quantum field theory after Arthur Wightman, where now unbounded operators appear. At this point, I'd like to mention that in the 1950s, when Arthur Wightman formulated his he tried to make a relativistic quantum field theory rigorous. He didn't know anything about unbounded representations, really. It was only, I think, a couple of years later in the 60s that Ullmann came along, and Bochers, especially Ullmann, and he managed to see that all of these axioms could be reformulated in terms of unbounded, in terms of locally convex algebras and unbounded representations of these algebras. And it is from there then that people started investigating unbounded operators and unbounded operator algebras and their representations on locally convex algebras more actively. One of the questions now is, what sort of unbounded operator algebras are we to work with? One thing is that bounded operators are very clear-cut. So they are everywhere defined, they are bounded, they are continuous. But unbounded operators, they are densely defined. And various notions which we take for granted in C star or von Neumann algebras, they take on more than one possible generalization in the unbounded world. And then they all turn out to be equivalent when you consider them in the special case of a bounded operator algebra. But they are not equivalent in the general unbounded case. So that can make things rather more complicated. But so this is now what I want to talk about here. So the first is I'm going to now just introduce the general terminology to try and home in on that. Here already is the symbol which I spoke about earlier, or linear operators with domain D. So you've got that X maps D to D. D is in the domain of X star, and X star maps D to D. And then this thing defines the involution. And it turns out to be a star algebra. One thing we are going to do also is to think of this L plus of D as some kind of an analog of B of H, the bounded operators in a Hilbert space in the unbounded world. And then an O star algebra on D is a star subalgebra of L plus D, which contains the identity operator. For those of you who are familiar with the literature on the O-star algebra, the O-star algebras, another name for these are also the OP-star algebras, which are the terminology due to Lassner. In case you are familiar with that terminology, they are actually the same thing. So one can sort of like think of L plus D as like a generalization of B of H in the unbounded world. But the operators need not be continuous. Well, if they would be, then you could extend them by continuity to H, and then of course you just get bounded operators all over again. Now, the commutant can be a bit of a tricky thing to work with. There are various notions of a commutant of unbounded operators in the unbounded world. When you restrict attention to the bounded operators case, they're equivalent. But it's not so obvious. There's of course the obvious one when you define the commutant in the unbounded world is to say, let's say, if you consider let's say we consider a von Neumann algebra in B of H. Let's just say. And now you want to look at when is T in the commutant of A. Then we already know, okay, let's say AT equals TA for all A and A. And then one can generalize this verbatim to the unbounded world. But that somehow turns out to be not really very applicable to the theory and especially to the physical applications. So other types of commutants have actually been considered. And especially those which would make them more applicable to what we call quasi-star algebras. So if we now take an arbitrary O-star algebra, so that's of course contained in L plus D, containing the identity operator. There's another type of commutant which we will be concerned with, and that is all bounded. Now it's bounded operator Z, so that when you take Z, take the inner product with XC, and you take the inner product with eta, then that's the same as applying first Z to Xi, and then taking the inner product with the adjoint of X to eta. So this is another type of commutant that one can work with, and there are at least 6 others to my knowledge. I can't necessarily offhand remember what they all are. But then if you want to consider a type of bicommutant, you would then look at all X in L plus D. Now we're coming to unbounded operators. This one consists of bounded operators, but now this one can consist of unbounded operators. But now in such a way that Z, it's defined via a similar formula to that. But now Z you take inside the weak commutant, the previous line, instead of M, and you take C and eta to be in D. We will restrict attention to that. And then also just the notion of a closed O-star algebra. So an O-star algebra take one on an inner product space. We can also define what is called the graph topology on D, but it's dependent on the O-star algebra under consideration. D is generally independent of the O-star algebra, but now we will define a topology on D which is dependent on the O-star algebra under consideration. So that's why I write relative to M. It is the locally convex topology on D defined by a family of seminorms as follows. So Xi is in D and it's indexed by an operator X in M within the O-star algebra. And that will be defined as just taking the norm in H of X applied to Xi. So that's the norm in H then. And we notice here that all these seminorms on D are indexed by the operators in M. So one can see it's dependent on what O-star algebra you take on D. And we will say that M is a closed O-star algebra if D is complete with respect to the graph topology coming from M. So in other words, we have the graph topology defined by all these seminorms, and then should it be complete, that means all Cauchy in M converge to an element in M with respect to this topology, then we call it a closed O-star algebra. Now we come to the main tool which we will use as the unbounded generalization in the local net approach. We start with a closed O-star algebra. We will call it a GW star algebra, and this is short for generalized W star algebra. So it's a generalization of a von Neumann algebra. If first of all the weak commutant, remember that this weak commutant consists of bounded operators. So if the weak commutant maps D into D, and if the bicommutant, which I've defined previously, so it's these things here, is going to be equal to M. This here is a generalization of the bicommutant theorem characterizing von Neumann algebras. And these type of algebras were considered sometime in the 70s by Prof. Atsushi Inoue. He considered and investigated these, and he found that this sort of structure was useful to consider Tomita Takasaki theory in the context of unbounded operator algebras. So this was actually very well suited to that. One might wonder why does one not just say M is equal to, let's say, the ordinary bicommutant, like we have, let's say, in the von Neumann case, which we are all familiar with. The reason is it's a little bit too restrictive. So one works with this type of bicommutation condition. In the case where all of these are bounded operators, then this is going to collapse to the normal bicommutant theorem that we know in the von Neumann world. Before I give some examples, just one proposition. If we have a closed O-star algebra in such a way that this weak commutant will map D to D, then this closed O-star algebra will be a GW star algebra precisely when M is actually all X in L dagger D, whose closures are affiliated with this sort of thing here, and this thing is actually a von Neumann algebra. This can be shown to be a von Neumann algebra. And so then you're looking at the closures affiliated with that von Neumann algebra. So if you know this, then it will be a GW star algebra if you have this. So it's looking a little bit like working with measurable operators and so on, a little bit like that. Okay, some examples. L dagger D will be a GW star algebra when this is a closed O star algebra. The second type of example will be what we call the EW star algebras. Again, this is another notion of an extend of a generalized of a von Neumann algebra, and they are more closely linked to what we call the generalized B star algebras considered by Allan. So that will be an EW star algebra if the closure of MB, so that's all X bar in MB, where this MB is just the bounded operators. These are just all the bounded operators in M. So MB bar is the closure of all X with N in MB is a von Neumann algebra in B of H. And then the commutant of this closure B, now that's in B of H, will take D to D, and you've got the affiliation property. Okay, these have also been closely have been investigated. And then thirdly, the example I'm also going to come back to again later on is if you take a properly infinite von Neumann algebra, that is a von Neumann algebra having no non-zero finite central projections. So no non-zero finite central projections. In a commutative von Neumann algebra, all projections turn out to be finite. So a properly infinite von Neumann algebra, it's very far from a commutative von Neumann algebra. And then of course the type 3 algebra is where you have a no non-zero finite projection. So those things are as non-commutative as you can get. Then one can actually show that if you take the set of all X and L plus D whose closures are affiliated with A, they are affiliated now with this properly infinite von Neumann algebra. That will be GW star, and it will also have this additional property that if, remember that with the GW star algebra, this is really like the, if I can say, the hidden von Neumann algebra, and that's just the same as A. And the domain D will be the intersection of the domains of all A, H to the N, where H is some self-adjoint unbounded operator affiliated with that same properly infinite algebra. This example I will refer to again. It's going to be one of the important examples. So I thought I'd mention just these examples for this talk. So these will also prove to be a good setting for that. So now we come to how on earth are we going to make sense of local nets, which will eventually also incorporate the Wightman theory. So first we need the definitions. The definition is going to sort of like mimic the bounded operators case, except for the bit with the space like separated, where one has to think more carefully. The first condition is like in the von Neumann case, where if you've got a bounded open region, the one contained in the other, then again you've got the one GW star algebra being contained in the other. And the other condition is again that you have a unitary representation of the Poincare group, where once again one has this. in the von Neumann case, then these were just the von Neumann algebras the corresponding von Neumann algebras. And we also have that. And the usual properties we've got here, and also with the joint spectrum. Okay, now the question only is how on earth are we going to handle space like separated where the commutants are involved? That is now where the definition departs from the von Neumann case. And one has to take care. In the von Neumann, we use the ordinary commutant, but now we have to try and invoke things in such a way that it's compatible with the commutant in the GW star definition. So then I thought about the following, that O1 will be space-like separated from O2 when the first GW star algebra will be contained in the strong star closure of the commutant restricted to D. And this strong star closure is in L dagger D. The strong star topology is again this topology on L plus of D, which can be thought directly of a generalization of the strong star topology in B of H. So you can have, for example, so what we then have is you've got something like the norm of xc plus the norm of xc star, sorry, yes. Like in the bounded case, but now except that the operators are now inside the unbounded operator algebra. We recall that this here is a von Neumann algebra, but we restrict them down to the domain D. And we remember, of course, this definition does make sense because this thing does actually map D to D. I can just take you back again. Oh, I'm sorry if I'm mentioning back like this. So it's because of this part that it will actually make sense. And that's part of the definition. So that this is actually, so it will map into D again. So it makes sense to consider this in L dagger D. And then likewise, we have MO2 contained inside the tau S star closure here again. So this is meant to generalize that the one algebra sits inside the commutant of the other, etc. Now you might wonder, but why on earth am I thinking of it like this? What was my motivation? Where did this come from? So next slide, I will try and explain it more. Okay, so let's quickly compare the von Neumann case. We know von Neumann algebras satisfy the bicommutation property, so we have that. In the GW star case, the bicommutation property now is this. So here RO is a GW star algebra, here it is a von Neumann algebra. Here, when we talk about the commutant, then it's going to be the weak commutant restricted to D in the GW star case. So when we now compare the two over here and we want to make sense of this in the unbounded world, then we take the bounded, so this is now a GW star algebra containing unbounded operators. We now take all the bounded operators sitting in here. And now we say, okay, this is like this thing over here, and this is now contained inside this commutant. Okay, now in order to go from here all the way to the unbounded world, we have to take the strong star closure of that. The strong star closure of this thing, the bounded operators in here, will be this. And so therefore that will be contained inside the strong star closure of that. So that's where the motive where the motive comes from if you actually go and you compare these two things side by side. And notice what we have inside these brackets here where we take the commutant, it is this. Notice what we have here, it is this. So that's where the definition came from. That was my motivation for it.
Sorry, can I have a question, please?
Yes.
Your commutant still they are bounded operators, right? From D to D.
Um,
But still they are
yeah, the
bounded.
original, yes, the original weak commutant. That one will be the if you take the first one, yes, that will still be bounded operators.
If you take it strong, this closure T tau and star, they may be unbounded, right? Or they're not necessarily should be bounded yet.
Yes, these things are bounded, but
Yes.
now you're taking the strong star closure in. You are taking it in L plus of D. So then
Yeah.
when you do that, then of course unbounded operators can start coming in.
Okay. Okay. Yeah. Yeah. Okay. I got it. Thanks. Okay.
So yeah, thanks for raising that question. So yes, that here we're taking the strong star closure in here. So when you take the strong star closure, then suddenly unbounded operators will be included. So you are including unbounded operators to close it off in the strong star topology. And that will again gel with the fact that these things are unbounded operators. So then this will contain unbounded operators. Okay, now one might think, okay, but is this definition, is it making the right noises? Is it well behaved? Does it actually agree with at least with certain physical scenarios? So in order to investigate that, I looked at a local modification of states. And before I start, I just want to lay emphasis on the first bullet. For purposes of relativistic quantum field theory, one should work primarily with type 3 von Neumann algebras. So that has actually surfaced, whereas because type 1 algebras are too restrictive. I read a paper of Jakob Ingvarsson in which he some years ago, before I embarked on all of this, in which he explained it very, very nicely. Then we recall that if M is a GW star algebra, you can write M this way. We will say M is a properly infinite GW star algebra if this von Neumann algebra is properly infinite. So in other words, that von Neumann algebra. Okay, let us take a properly infinite GW star algebra in such a way, that's MO, in such a way that it's corresponding von Neumann algebra. So when you look at what the operators are affiliated with, that they map D to D. So I'm working with one like that. Then one can show that one can get a partial isometry inside this von Neumann algebra, call it W, so that W star W is 1 and W star W star, let's say, is E in here, the same algebra. And if one then takes a normal state on L plus D, and now you define a new state where that W sitting here is the partial isometry W in the previous line, and that's equal to phi of W star XW. Then C is another normal state on L plus D. So here I'll just want to say that I'm leaving out some detail here. A lot of this can be shown, but I've left some detail out. Just the technicalities, and I summarize it here. But in my paper, I've given the details. Then if you take, and if for that same normal, if you take that normal state and you put it in over here, remember E is this projection here. Then of course this is C of X, that's an easy thing to show. And then if you take Y to be in the strong star closure here, then phi WY is equal to phi of Y. Okay, so basically, oh, here's the slide. Okay, I nearly thought okay. So the second last bullet is actually saying that you can then take another normal state and you can therefore actually sort of like change it from the original state phi by using this element, which can be shown to be in RO. There's one thing that I wish to mention here, and that also is that it can be shown here that this thing is necessarily in MO. That can actually be shown. So it's almost like you take another state and then you are almost like you are preparing it from this one. But now if you now take something which is in a region which is space-like separated, so we take the strong star closure, then nothing changes. Then phi of y is still phi wy. So it doesn't look like. So you can change. You can alter the state phi if one can refer to it like that within MO, but outside in a region which is space-like separated to it. The last bullet, then you can't change it. So that seems to agree with the fact that from the one region to the other, well, they are separated because otherwise you need faster than light travel. So that seems to then suggest that there seems to be a reasonably good definition, especially for the space-like separated. Also, I've put this restriction here, but that can actually be quite a severe restriction. And the reason being is because one can show that if you take a properly infinite GW star algebra on D, which doesn't, let's say, which doesn't satisfy, or no, one thing I can say why it's a severe restriction is that then the operators actually turn out to be bounded operators. So that's why it's severe. So if one can maybe try and ease that restriction a little bit, if instead one considers something like this, which does not necessarily satisfy that, in that you can then get W in here, so that W star W is 1, and again E in here. And then also if W restricted to D is an L plus of D. And this, especially this last part here, the W restricted to D being an L plus of D, this did not occur in the previous part here. This didn't occur there. So if we try and tweak things like that, then we can avoid having to make such a restriction. And then you can still get these two conclusions here, that you can sort of like prepare one state locally from the other, but not in the causal complement. So yeah, one should try and make sure one should try to check that those things actually make sense, that it's a good definition. Now we want to look and see how we can actually combine the Wightman field theory with the local nets. Let's first look at a definition which goes back to Bocher's. A Wightman field of operators is associated with the local net of von Neumann algebras if the Wightman field operator extends to a closed operator on H for all F. And we will also have that the closure of F will be affiliated with that RO, provided we know that the support of O is contained in O. Support of F. Sorry about that. Support of F is contained in O. So if the support of F is in O and you put that F here, then the closure of phi of F is affiliated with RO. That's when it's associated. And in other words, what we have is that we've actually got that the spectral projections for the closure of phi of F will then be inside the von Neumann algebra. Okay, this goes back to Bocher's, and then one can prove a proposition that if you take a local net of GW star algebras and you take this sort of thing, which is a Wightman field, satisfying that. Wait, so yeah, what I mean. And when that you've got this in R13, we have phi F in MO. Oh, no. Sorry, what have I done here? That should be the support of F contained in O. Yes, that's what it must be. Sorry. Okay, I don't know what went wrong there. Okay. And now what? So in other words, we are assuming that we've got a Wightman field for which the support of F is contained in O, that if we have this, we have phi of F in MO. And we assume that the local net will also satisfy this condition. Now we suppose that the supports of F and G are such that the support of F is inside this region and the support of F is inside this region, and we assume that O1 and O2 are space-like separated. Then one can show that the phi of F and the phi of G necessarily commute. So that is the definition. And so, okay, so there one has to apply the definition of local net, including the way in which I defined the space-like separated. So then the definition of space-like separated in the sense of the definition of local nets of GW star algebras appears to be consistent with the definition of space-like separated in the Wightman field theory sense. Because in the Wightman field theory sense, we defined the space-like separated using that commutativity condition of the Wightman field operators. So that's another reason why I proved this proposition, to check how good is this definition. Okay, maybe, all right, although I at least have half an hour, maybe just in the interest of time, maybe I will just skip something. I will skip the proof. Okay, just to make sure I get done within the next half an hour. Another proposition here that one can show is that if you have a Wightman field of operators which is associated with a local net of von Neumann algebras, so that means that, so you've got the affiliation property again under certain conditions. For every bounded and open region here, we will we will define MO like this. Again, all X and L plus D for which their closures are affiliated with the von Neumann algebras RO. Then for every bounded and open region, assume that this is an EW star algebra on D. Then if the support of F is contained in O, then phi F is, one can show that phi F is an element of MO and every MO is a GW star algebra. And furthermore, not only that, one can show that this is a local net of GW star algebras. So, okay, to show that, okay, one actually has to sit and write out the details. So you have to actually go and show all three conditions. So you first have to show that this is indeed an GW star algebra, and then that you get the local net approach, you need to show the three conditions. And that's under the assumption that that is an EW star algebra. So then at the same time, one does also have an example of a local net. This example I might say a little bit more on shortly. Okay, here we go. Here's the slide again. If in proposition 2, we instead assume here that the commutant of the von Neumann algebra, so these are von Neumann, maps into D and in such a way that this is just MO. In other words, instead of assuming that MO is an EW star algebra, we have these two conditions. Then if MO is a closed, then MO is also a GW star algebra. And one has that this commutant is that. So remember, MO generally is all X in L plus of D. For which then X bar turns out to be affiliated with MO prime W W. And now we are saying that this thing actually then is the original von Neumann algebra which we have started with. And then this can be shown to be a GW star if you don't want to have the condition of EW star algebras, but instead you have those conditions. And then one can argue like in the previous proposition. Okay, yes, that was the example I had mentioned earlier. We return to the case of a properly infinite von Neumann algebra, which is more interesting from the relativistic point of view because every type 3 algebra is properly infinite. So now I'm taking a self-adjoint operator affiliated with RO for all of that. We take this DH and we again consider this the usual affiliated type operator algebra. And then as in the previous example, then one can again show this is another local net of GW star algebras. So also now these, maybe I want to just go back. That's something I wanted to say. Now I remember what I wanted to say. Is that actually now the local net of GW star algebras provides a home for both the local net approach as well as the Wightman field operators. The Wightman field operators belong to the local net as well as then the underlying von Neumann algebra. So you've got this unifying structure that actually combines both of them. Previously, Bochers and them, they have not considered they've considered the two theories separate because I think they were uncertain as to how to navigate with the unbounded operators. And the affiliated operators do generally not form a star algebra unless you're working with a finite von Neumann algebra. So if you place just a few more kind of restrictions, then you can get the affiliated operators or a subset thereof to be a star algebra. So now that the Wightman operators and the von Neumann algebra are like elements of the same algebra, now one can actually use that topological algebraic structure and work with these things like you use the topological algebraic structure in a von Neumann algebra. And now at the same time, one can actually see how to work with the Wightman field operators. Because previously, the Wightman field operators, they just float around the von Neumann algebra. And you don't really know how to actually combine it with the algebraic structure. Okay, maybe I just want to emphasize again. In general, if you look at all affiliated operators with a von Neumann algebra, that need not be even a star algebra unless the von Neumann algebra is finite. But now we look at more restrictive type conditions under which affiliation occurs, and then it can become a star algebra. So it actually creates this unifying structure for both. So it's almost like you enlarge your local net of von Neumann algebras to swallow the Wightman operators. One thing that I've also considered, and this actually provided for me the motivation to work with these GW star algebras, but I thought let me mention it toward the end. That if you take two GW star algebras, how do we consider product states? I'm going to now make these two assumptions here, which I must confess, I mentioned earlier, is quite restrictive. It can be quite a restriction. So, and then M1 and M2 turn out to be EW star. Now, a few years ago, it was a professor in Norway and Professor Fragolopoulou also in the audience and myself. We actually looked at tensor products of these GW star algebras. And so we had a paper published, I think 10 years ago, 11 years ago in the Rocky Mountains Journal. That feels to me like yesterday, and it's now 11 years ago. All right, so I've actually used those ideas on the tensor product here. What one can do is consider the usual tensor product of D1, D2, and then take the closed O star completion of D1 tensor D2. And on that, now we can form a GW star algebra which generalizes the von Neumann tensor product. And because of all the conditions which I've put here, then one can show it's unique, and that's what we've done in our paper. There were actually 3 different types of tensor products which came up. But okay, I wanted uniqueness for obvious reasons, so I considered this rather more severe restrictive case. So now we have even more examples of GW star algebras. Now the thing is, what can we take as a GW star algebra generated by M1 and M2 if they're on the same domain? If these two were von Neumann algebras in B of H, then you would take the smallest von Neumann algebra in B of H containing M1 and M2. But the problem is now when you work in L plus of D, this need not even be a von Neumann algebra. So now when you look at a von Neumann algebra generated in there, this might not be defined. So what do we do? So I then thought of, okay, maybe let's just try and take the GW star tensor product of M1 and M2, and let's actually take that as the as the GW star algebra generated by D1 and D2. Because in L dagger D, this generated GW star algebra, like in BH, might not always exist. So let's take that. And I'm assuming I've got uniqueness because I'm assuming all of those conditions.
Sorry, your all-star completion for the tensor product, where did it come from? I mean, there must be some algebra there, right? First, to define all-star completion on the tensor product, D1, D1
Oh,
tensor D2.
okay. What I actually meant was that D1, yes. So we look at the tensor, we look at the tensors on, let's say, T1 tensor T2, where the T1 comes from M1 and the T2 comes from M2. So we actually started with these operators, and then we formed that space from there.
Ah, okay, okay. Yeah, first of all, algebraic, just tensoring operators and then defining the topology.
Yes,
All-star.
that's how we
Okay,
did
okay.
that.
Okay, thanks. Mhm.
Thank you very much for bringing that up. I forgot to mention it. Okay, yes. If now M1 and M2 are von Neumann algebras, both on the Hilbert space, then the von Neumann algebra in B of H need not have normal product states, or it's generally difficult to determine whether it has normal product states. And actually, Buchholz had shown this in 1974. So he gave an example in the von Neumann case where the generated algebra the generated von Neumann algebra of two von Neumann algebras in B of H doesn't have a normal product states, and generally he highlighted the difficulty with one other example. But if you now actually look instead, and you think of this as your generated GW star algebra in the GW star world, then actually that problem will disappear completely. But of course, it comes at a price in assuming these two conditions, which I think are a little bit more restrictive. If phi1 and phi2 are normal states on M1 and M2, then there's a normal product state on that. Okay, so by product state, then I mean phi of x tensor y. So that will be the normal product state. Let's call it phi. What do I mean by that? Phi of x tensor y. Now we take phi1 and phi2. That will be this. Okay, so it's almost like the state phi is not entangled. It's not it's not an entangled state. And I've actually started the investigation with with the existence of the normal product states, and then I thought, okay, let's stick then to the GW star world. Because this seems to make the most sense. At least here we get a normal product state.
Maybe just product, because, well, what did you mean by normal state? It's a functional, right? The positive
Yes,
unit.
by a normal state, I meant something. Okay, I can elaborate on it here. So let's say phi1 is a normal state.
Yeah.
So it's very much like in the von Neumann algebra case.
Yeah, that then phi1 x times phi2 y, right?
Yes, yeah, that's right. So you tensor here, but then by
Yes.
normal,
No, no, on the right-hand side, it should be just times, is it?
oh,
So you
sorry.
had a product of two
Okay.
complex numbers just.
Yes, sorry, of course. I'm being very
Okay,
silly.
okay.
Thank you for pointing out. Okay, it must be very late on a Friday afternoon. Okay. Yes, thank you. Okay. All right. So then you would define a normal state in the same way like in the von Neumann case. Okay. Some just to make sure that I do not run out of time, I will then skip that here. One other thing I had also considered is, and okay, maybe this is rather very bold. I don't know if this is ever going to pay off, but nevertheless, I thought, okay, I was tempted to think about what it could be. Um, how would one actually consider a gauge group in this setup? And again, I've got no idea whether this will work, but okay, nevertheless, let's give it a go. We have a local net here for each bounded up open region O. Let's let UO here denote the set of unitary elements in the commutant of that von Neumann algebra. Then one can take that here to serve as a gauge group as it consists of local symmetries. So it's almost like those unitary elements or symmetries only apply within a certain region. So they can change from region to region. This looks perhaps like a natural definition, but there is a problem. This definition is too simple. What if you take U, let's say, to be SU2? Then the underlying Hilbert space is finite dimensional, and you will not have unbounded operators on the Hilbert space. Well, okay, it gets worse. This commutant then will turn out to be a type 1 von Neumann algebra. And of course, for relativity, we want the type 3 algebras. And the type of type 3 algebra that one usually takes is that hyperfinite 3-1 factor. Up to star isomorphism, there is only one hyperfinite 3-1 factor. So this definition is maybe not so great. So maybe how about this? And I'm nearly toward the end of the talk. C2 two-dimensional Hilbert space. So then if we then take then we know already that we can find a closed subspace of H so that this works. And here we identify C2 as a two-dimensional subspace of H. Therefore, one should rather just take that, direct sum it with I, where I is the identity operator on that space. Okay, so perhaps maybe one should think of some sort of a split property. And this has been considered in the literature. For every bounded open region O1, one can get a type 1 region, type 1 von Neumann algebra MO1, and a bounded open region O2 in the causal complement of O1, so that this happens. So it's almost like you got a type 1 algebra nestled within the type 3 algebras. If it's sort of like squeezed in the middle. And if you now consider any two bounded and open regions, now these need not be separated causally from one another, one has that. Then maybe this looks like perhaps a better definition to work with, especially since the split property does come up and has been well studied. Except my definition is slightly more restrictive because I'm working now with an arbitrary type 1 von Neumann algebra, and I do not insist that it be a factor. Lastly, I would like to mention that I wrote a follow-up paper to this which has recently been accepted for publication, and um, that's now in in press at the moment. It hasn't appeared yet. Okay, in which I try to investigate this whole idea with the Gorge group further. Just putting some ideas on the table. So this is basically now where I end. Okay, some references here, and then also here is the paper on the tensor products of the unbounded operators, which I referred earlier, which was written by Maria Fragolopoulou and Atsushi Inoue. Again, thank you very, very much for your attention. Are there any questions or comments?
There is another.
Questions, please.
Oh,
Yeah, concerning the normal states over L plus D, probably all of them, there comes from the B of H, right? They're all continuous.
Not
Oh,
necessarily.
not necessarily, right? So,
They can be defined, they actually can be defined on, they can be defined on L plus of D. So yeah, so we define them now on unbounded operators, unbounded operator algebras, but you can define them analogously.
okay, so by definition, it should be unitil and positive, right? So any functional like that.
Yes, that's correct.
Okay, and they are not necessarily should. Yeah. Okay. Okay, yeah, thanks.
More questions, please. Well, I have a question which is probably not directly related to your talk, but it is directly related to algebras of unbounded operators. So if we have an algebra of bounded operators, then it's well known that it has a natural structure of an operator space. Also, there is a natural locally convex generalization of operator spaces due to Effers and Webster. So my question is, do algebras of unbounded operators have a natural structure of a local operator space in the sense of Effers and Webster?
This actually is something I have not considered yet.
Hmm.
That actually, that of course is very interesting, but I have as of yet not yet thought about that. But yeah, that's an interesting question.
Mhm. Okay, thank you. Any other questions, please?
One more comment. You mentioned several times concerning joint spectrum of operators. What kind of joint spectrum did you mean there? Is it just a hard spectrum? If it's hard, it should be some algebra there, right? Commutative algebra. I mean, anyway, what did you mean by joint spectrum for operators P0, Pn?
Okay, the joint spectrum from P0 okay to Pn is where you take, for example, a sum of, let's say, uh, S, something will be in the joint spectrum if, let's say, you've got let me think. I just want to think about how to write it. If we consider only one operator, let's only look at one case, and we say, let's say lambda is in the spectrum of P0, then you are looking at whether lambda 1 minus P0 has at least some sort of an inverse. Okay, whether that can be invertible. So now what you want to do is you want to look at lambda 1 up until lambda n.
Yeah, tuple, yeah.
That's so you need to look at a tuple which is now in Cn.
Yes.
Yes. So then to consider that you would need to consider whether Lambda 1. Okay, let's make it consistent with the subscripts.
Yeah, no, okay, lambda 0, yeah. Mhm.
Yeah, so then you would say that thing, let's say, times some operator S0 plus lambda, I had Pn there, so okay, lambda n minus Pn times Sn, let's say, equal to the identity operator.
Oh, but but S0, Sn should be from fixed algebra, right? Commutative algebra. Otherwise, it's useless, I guess, because you mentioned probably Hart spectrum, Hart. But in this case, they should be fixed some commutative algebra, A, which contains all these operators. Or optionally, instead, you can look at the Taylor spectrum, but it's not Taylor. Whatever you mentioned here is something else, right?
Yes, that's yeah. So I think it's just that I don't think I think it is more or less something like that.
Okay. But you're not fixing some enveloping algebra, is it? There must be
No,
some
no.
commutative algebra somewhere.
At this stage, no, not that I can recall.
Okay, okay. So P0, Pn in general, they can be operators of infinite dimensional space, is it? They're not necessarily
Yes.
matrices.
Yes. Okay, let's quickly go back to the start.
Yeah, the self-adjoint commutative operators. Okay.
At this stage, I'm also considering it like in the generalized unbounded operator setup. So yeah, so I haven't necessarily restricted myself to a specific algebra.
Okay, okay. Yeah, anyway, I don't know. So in general, we have a Hart spectrum, which depends on algebra, or we may have a Taylor spectrum, then quite independent. What else? I don't know.
There are quite a number of spectra from what I do recall.
Yes.
But yeah, I think it's the simplest type one which does appear here. But
Okay,
again,
okay.
I didn't restrict myself to where those other operators S0 to Sn must come from.
Mhm. Okay, okay, yeah, thank you. Mhm.
More questions, please. Well, if there are no more questions, then we thank the speaker for the very interesting talk. Thank you. And
Thank you very much.
thank you very
Thank you.
much. I'll see you next Friday.
Okay, yes, I'll see you next Friday.
Thank you.
Okay.
Right.